So we're here for an exciting talk about mathematics of Rubik's Cube, and she explained it to her 9-year-old son. I give you Wendy.
Thank you, Dr. So many people come to my talk. Well, I didn't go out of my way to teach my 9-year-old son abstract algebra. It just happened naturally like this. So he was 9 years old when he got interested in Rubik's Cube. So I taught him a few moves so that he could solve it independently. And then he was just left alone to explore whichever way he wanted. He was fascinated. He would record his discoveries in his notebook. And I was pretty happy to see that. So one day I said casually, I don't know why I said it, but I said, well, you know what? There's a lot of math behind the Rubik's Cube. And I remember my son looked at me with this most puzzled look on his face and asked me, Mommy, I don't see addition, subtraction, multiplication, and division. What's the mathematics you're talking about? Tell me. How am I going to do this, right? But he was quite persistent. So at the end, I wrote everything out for him in this notebook. I deliberately left blanks within the text for him to fill in so that he could participate in the narrative. I also left 4 or 5 exercise questions after each section. So that way he was involved from the beginning to the end. It worked out okay. Before I tell you exactly what I told my son, let's first get the notation straight. So a Rubik's Cube has 6 faces. U for upper face, D for down, L for left, R for right, F for front, D for back. What does it mean by L as a move? L, this is a side. Okay. So you look at this L, you make a 90-degree turn clockwise, that's L. You make a 90-degree turn counterclockwise, that's L inverse. We also have middle layer turns, M, E, S. M is the vertical middle layer. You push it in towards you, that's M. You push it outwards, that's M inverse. E is the horizontal middle layer. You push it away from you, that's E. You push it towards you, that's E inverse. S is a clicking motion, like you're clicking a shutter. This is S. You bring it up, that's S prime. You can also reorient the whole cube. So X, Y, Z, that's what it means. X means you rotate the entire cube on R. That's X inverse. You rotate the entire cube on U, like this. That's Y. And that's Y inverse. Z, you rotate the entire cube on F. So that's Z. That's Z inverse. We also need notation to record our discoveries, right? So whenever you see me draw diagrams like this, that means upper layer. What happens with the upper layer? In this case, 3 corners are rotated. In this case, 2 pairs of edges are rotated. And then I want to follow which piece goes to where, right? So I name all the corners and pieces in my own way, quite randomly. So the corners are named from A through H, and the edges are named from 1 through 12. Okay, now I can start. Remember, my son at that point knew more about the cube than about math, right? So I would build on what he already knew. For example, he already knew how to say rotate 3 specific corners. So, okay. Now, what if you want to rotate random three corners? Okay, what do you do, right? Now imagine you have an object, you want to draw a hole here. The object is on the production line, and the draw is directly above the production line. What do? You first turn the object right, and then you draw the hole, and then you undo the turn right. What you just did is called conjugation. Conjugation. So GH inverse, G inverse is a conjugation of H. H is the main thing you do. But in order to do that, you do some preliminary moves, G. And then after you do H, you undo G, right? That's conjugation. So likewise, if you know how to swap two pairs of edges like that, you can swap any two pairs of edges. And then next, I introduce them to commutator. Commutators come in the form of A, B, A inverse, B inverse. Like for example, if you do A out, A, that's a commutator. Now restore it in 4 steps. It's not easy. That's not easy because typically commutators involve a lot of pieces. If you work with, say, skewed cube or pyramid-shaped cubes, you observe what commutators do, you pretty much solve it. People use commutator to design algorithms. It can work like this. So when you're doing A, you work on a spot. And at the same time, you disturb some spots that you will later restore. And then B brings another piece to the working spot. Then A inverse continues to work on the spot, and then at the same time restore what you disturbed earlier. Then B inverse just undo B. For example, this one. U inverse L inverse U R U inverse L U R inverse. This one works in the way I just described. And do you see it's a commutator? For algebra. And when you do inverse, you backtrack, right? The inverse of U inverse L inverse U is U inverse L U. Right? That one, the next result is this. It rotates 3 corners in the upper layer. Before I got serious with math, I wanted to write something to delight my son. So I talked about God's number. What is God's number? Okay, do you believe that with every configuration, you have a natural number associated with it? That is the amount of steps required to restore. You probably don't know that number offhand. You can fix the cube. You most likely use more than the minimum amount of steps to restore it, right? Nonetheless, that number exists somewhere out there, right? Now you have this million number of configurations, 43 quintillion. Each configuration has such a number associated to it. And now you have 43 quintillion numbers out there, okay? Do you agree that among them, there is the biggest? And that one is God's number. So God's number is the maximum size of minimum solution. God's number can come in can come in more than two, can come in different metrics. So one is half-turn metric, where every half turn, every 180-degree turn is counted as one turn. And then it can also come in quarter turn. Quarter turn metric. So every half turn is counted as two turns, right? It used to be a big deal, but now we have the answer. So the answer, God's number for half turn metric is 20. For quarter turn metric is 26. Now, which configuration has the honor of being the first one to be proven to need 20 turns in half turn metric? It's this one. It has a name, it's called Superflip. What does it do? Does nothing other than flipping all the edges. These four algorithms all give you Superflip. They're more than that, and this gave you four. And this one is the holy grail. If you count the 20 steps, that's the one. This one involves middle layer turns, so it's interesting. This one is a little longer, but it's very symmetric. It's actually easy to memorize. And I personally like this one the most because it's the most symmetric. Let's do it together. So M, U inverse, do it 4 times. 2, 3, 4. And then this is Y, this is C inverse. 1, 2, 3, 4. Y, Z inverse. 1, 2, 3. Okay, I didn't mess it. All right, that's Superflip. Superflip has an interesting property. It commutes with any other configuration. Think about it, if you do your thing, and then you flip all the edges, it's the same as you do your thing on a cube whose edges are already flipped. Do you think there could be another configuration that have this property that commutes with any other configuration?
Other than the identity, I assume.
Other than the identity, yes, good one. So in order for that to happen, you have to act on this cube evenly, global-wise speaking, right? If you rotate corners or rotate edges, it's not going to be globally even. If you twist corners, it's not going to be globally even. So Superflip is your only shot. Now, which configuration has the honor of being the one that requires 26 steps in quarter turn metric? Actually, there is only this one, single one that's known to us. This one. And it's this one. Looks like Superflip, huh? On top of superflipping every edges, it swaps 2 pairs of centers. This pair of centers are swapped. Is swapped, and this pair of centers is swapped. It also has a name. It's called Superflip with fourspot. Fourspot, one word with no plural S. what happens if you do superflip and then do this? What happens? You get 4 spots, right? There's no name for it, but I call it 4 spot. Now, the commute. So there is something in common among these three. There is something in common. If you do every single one twice, what do you get? So each of these three has order 2. All right. Now let's get serious. So next, I introduce the concept of permutation and the notation of permutation to my son, because I wanted to answer a question, which is what will happen if you repeat an algorithm again and again and again and again to the end of the word? What will happen? Well, the answer is quick. You'll get identity, right? But why? All right. Let's take a look at an example. What happens when you do F2 R2? I don't need to show it to you, but in terms of corners, it has 2, 3 cycles. BDG means B goes to D, D goes to G, G goes back to B. And then in terms of edges, it has a 3 cycle and 2 transpositions. If you do it twice, the transposition will vanish, right? If you do it 3 times, all the 3 cycles will vanish. If you do it 6 times, all brackets will vanish, you get your identity back, right? This is the case where only relocation of pieces is involved. There's no flipping of edges involved, there's no twisting of corners involved, right? Sometimes you have a 3 cycle of corners. You repeat the algorithm 3 times. You do get the 3 corners back to their original locations, but each of them might be twisted 120 degrees. So you need to do 9 times to get it back, right? All right, let me give you another example. That one is interesting. That one gives you 3 cycle of corners, 5 cycle of corners, 7 cycle of edges, and then transposition of 2 edges and another 2 edges. So in this case, the first 4 brackets all involve reorientation. So the order of this cycle, meaning how many times you need to repeat to get back to the identity, is not 3, it's 9 instead. And this one, it's not 5, it's 15. This one, it's 14. This one, it's 4. This one is 13. So the least common multiple of these is 460. That's It's an interesting number because you're not going to find any other configuration that requires more than this many of times to repeat to get back to the identity. This is not the only configuration, there are others. I'm just giving you an example. Now, the third example will help us understand the cube better. What if we do lowercase u, lowercase r? Lowercase meaning double layer times. Like, instead of grabbing just one, the top layer to do u, you grab both the top layer and the middle layer, you do u, that's lowercase u. So you might ask, well, why do we need that? Isn't lowercase u just d? Isn't lowercase r just l? Right? If we do dl, we will get 5, 7, 8, a cycle of 7 corners, a cycle of 5 edges, and then one. A cycle of 7 edges, a cycle of 5 corners, and then one corner is twisted clockwise. So this one has 7, this one is 5, this one is 3. After we do 105 times, we get back to identity, right? But it's very weird if you do lowercase u, lowercase r 105 times, it's still very chaotic. So what happens is when you do it 8 times, there are 3 cycles, the edges and corners are flying around. But what you see is 3 centerpieces are rotated. O goes to F, F goes to D, D goes to L. So you do it 24 times. You do it 24 times, then it looks neat. A, B, C, G, E. It's the rotation of 5 corners. 25 times, 24 times 5, that's 120. After you do 120 times the lowercase u, lowercase r, instead of 105, you get factorial. Now I have a little more things to say about permutation. Each permutation can be written as a string of transpositions. For example, 1, 2, 3. What is 1 to 3? 1 goes to 2, 2 goes to 3, 3 goes to 1, right? Is equal to you swap 1 and 2 first, and then you swap 1 and 3. And that's how the notation goes. You read backwards. So let's double check. 1, 2, 3. Swap 1 and 2. Swap 1 and 3. It is the same, right? Now, likewise, if you have 4 elements involved, you have this. That's not the only way to rewrite things in terms of transpositions. For example, this one can be written as you swap 2 and 3 first, and then you swap 1 and 2. That's also 1, 2, 3. Actually, there are infinitely many ways to rewrite a permutation. Always add more transpositions. Right? And the amazing thing is, there are infinitely many ways to rewrite a permutation. Either all of them need an even number of transpositions, or all of them need an odd number of transpositions. So in the former case, the permutation is even. So this one is. This one is even. And in the latter case, it's odd. In terms of Rubik's Cube, for example, if you swap two corners and two edges, that's even or odd permutation. You have two swappings, right? So that's odd. You might have, you can rotate four corners. And then swap two edges. The four corners, that gives you the odd permutation. And then you swap one pair of edges, so that's still even, right? Now it turns out that all the configurations you can get are even permutations. Why? Because each turn you make, whatever turn you make, if we number the edges and corners, what happens is 1 goes to 3, 3 goes to 5, 5 goes to 7, and 2 goes to 4, 4 goes to 6, 6 goes to 8, right? And this one is odd. This one is odd. That gives you an even permutation. So each term results in an even permutation. So whatever you do, you always get an even permutation. And that piece of information is important when we are trying to figure out that huge number. How do we get this number? How do we get this number? Now imagine you just assemble the whole cube, and then you assemble every piece together. Okay? Imagine you're blind. You just blindly assemble them. How many possibilities do you have? Or you have eight corners to locate, right? That gives you 8 factorial. You have 12 edges to locate, that gives you 12 factorial. And then each corner you have 3 different ways to orient it. Each edge you have 2 different ways to orient it, right? So that gives you 3 to the 8th and 2 to the 12th. That's with just no restriction. Okay. But we are restricted because we are trying to assemble a solvable cube, aka a normal cube, right? So what is the restriction? We just said it must be even permutation, right? So we need to divide it by 2. There's an equal chance that you get even permutation or odd permutation. Why? Imagine you already assembled all the edge pieces. Okay, so the edge pieces having odd or even permutation, that's already determined. Now in your hands, you have the 2 last pieces of the corners. You put them down one way, it's even. You put them down the other way, it's odd. So the chances are half. You divide it by 2. You need to divide it by 2 more factors. Because when you are orienting the last piece of corner, you are not free. It's forced. You have to put it a certain way. Okay. When you're putting down, when you are orienting the last piece of edge, it's forced. You don't have choice. Which means you cannot have a cube where only one edge is flipped. That will never happen. You can possibly flip two edges. That's possible. You cannot twist one corner. You can possibly twist two corners. One clockwise, the other one counterclockwise. The Rubik's Cube has so many configurations. But there is a concise way to write it. It's generated by these basic moves. Now. The interesting thing about it is you don't have to have all six. You don't. Specify anything or not. If I wipe that E out, it's perfectly fine. Because this one gives you D. This one has only the other five, right? But if you do it, it gives you D. Or this talk is being recorded for those audience who are watching the video. I'll put them down in the description. Don't worry about it. So you can rewrite it in that form. Does that necessarily mean that the Rubik's Cube has to be generated by 5 elements? It just means it's generated by at most 5 elements. Could there be a set of 4 very strategic strings of moves? I don't know. If you have information about that, please let me know. All right. So now I can tell my son exactly what Rubik's Cube is as a mathematical object. It's a group. It's a permutation group. So a group is a set plus an operation that satisfies 4 criteria. Number 1, it's closed under the operation. Number 2, the operation is associative. Number 3, there's identity. Number 4, every element has an inverse. So what's the operation we're talking about? The operation we're talking about is followed by. So a string of moves followed by a string of moves is still a string of moves, hence the closeness. You do 2 moves followed by a third move is the same as you do a move followed by 2 other moves. Right? The restored state is the identity, and for inverse, you backtrack, you get inverse. So let's think about it. Okay, so moves results in a configuration, which can be described by permutation. So you can think of the Rubik's Cube as moves followed by moves, or configuration followed by configuration, or permutation followed by permutation. It's fine either way. But really, it is permutation group. It's a subgroup of S54. Next, I introduced the concept of group isomorphism to myself. Isomorphism is a big word for him, so I have to write it out. Group isomorphism. So loosely speaking, if two groups behave the same way, even though the elements are called by different names, are isomorphic. Let's look at a group. This is a group table. E, A, B, C, 4 elements. E is the identity, so we just copy verbatim. And then this group looks like a conveyor belt. After E, A, B, C, it's A, B, C, D, B, C, E, A, C, E, A, B. That's a group. You can check it satisfies all 4 criteria. Here we have another group. If we do addition mod 4, 0, 1, 2, 3, 0, 1, 2, 3. 0 is the identity. Copy. 2, 1 plus 2 is 3, 1 plus 3 is 4, but mod 4 is 0. 2 plus 3 is 5, which equals to 1 mod 4. Well, they behave the same way, right? In the cyclic way, right? So E is our 0, A is our 1, B is our 2, C is our 3, right? They're just being called different names. So these two groups are isomorphic. Now let's look at another group that also has 4 elements. Copy. In this case, every element, you do it twice, you get back the identity. So on the diagonals, they are all E. And then A times B gives you C, A times C gives you B times A, C times A. Obviously, this group doesn't work the same way as this one, right? These two groups are not isomorphic. So this one is cyclic group of order 4. This one is pi 4, denoted B. But these two groups have something in common. Every element commutes with all the elements of the group. A group with this property is called abelian. So it's Rubik's cube abelian or non-abelian? Has to be non-abelian, right? Because simply you do UR, it's already different from RU. Okay, now let's take a look at what interesting subgroups that Rubik's cube group has. By Lagrange theorem, the order of a subgroup has to divide that in the whole group. Right? So we have factor 2, 3, 4, there's no 5, there's 6, no 7, there's 8, and so on, right? So now, what subgroups have order 2? Order 2. We already have them here, right? This one has order 2. Or this one, the one that flips 2 edges, has order 2. Or these. Or these, right? Order 2. And this one I saw it's pretty cool. U R L U 2 R inverse L inverse. This one, if you do it at first glance, you wouldn't guess that you just need to do it twice to get back to identity. It looks like a lot of things are playing, but it actually swaps 3 pairs of edges and 3 pairs of points. That's pretty cool. Now, what group has order 3? I tell you, my son's favorite group of order 3. Orally. R2, D2, R inverse, U inverse, R, D2, R inverse, U, R inverse. This one rotates 3 corners on the front. He loves it because it has R2, D2, like in the stories. Now this one should have order 3 too, right? It twists 2 corners. What subgroup has order 4? That's easy. You do F, F2, F3, also known as F inverse. F4 gives you that identity. So that one is 4, right? The group generated by F is isomorphic to 4. You think of any group that's isomorphic to this one. Identity, superflip is four spots, they form a group that's isomorphic to prime 4, right? Can you think of another prime 4? Do you get any inspiration from him? What happens when you do E2 twice? What happens when you do S2 twice? What happens when you do E2, S2 twice? So the group generated by 2 and S2 is isomorphic to prime 4. Now, which subgroup has order 6? We encountered it earlier when we talked about repetition. The subgroup generated by F2R2 has order 6. That one, the 2 cycles vanishes, the 3 cycles vanishes, that one. And what subgroup, what canonical group of order 4 do you have in mind? We'd be excited if we're going to see quaternion. A concrete quaternion group in your hand, right in front of your eyes for you to see. So let's have a recap. What is quaternion group? Quaternion group has 8 elements. That satisfies I squared equal to J squared equal to K squared equal to -1. Ij equal to K, Jk equal to I, Ki equal to J. And this is not a video, right? So, if we design it, do you have any idea what should be -1 for simple? Superflip. Superflip. How about this one? The upper layer, okay? Flip all 4 edges on the upper layer. Does that look like a good candidate for negative? For I, swap these 2 pairs, and then you flip these 2. You can mix it, you do it again, you get -1. After 2 repetitions, these swapping vanish, right? But then the second time when you do it, you bring this piece to the walking spot, right? So all four edges get flipped. Now in the same flavor, J looks like this. That gives you J. That's J. So now we can figure out what K looks like. K is IJ, right? K is IJ. So this edge goes here first and then it's brought here. So these two edges are swapped. And this one first goes here and then goes here. So it goes there, right? These two are swapped. I'll let you convince yourself why these two are flipped, okay, while I give you the formula for I and J. So the subgroup generated by I, where I is F2 M inverse U inverse M U inverse M inverse U M U F2. J is F U2 F inverse U inverse L inverse B inverse U2 B U L is isomorphic to the quaternion group. Isn't that something? Oh, by Lagrange theorem, how big can a proper subgroup ever be? It can be as big as half of the group. We have such a big subgroup in Rubik's cube. Earlier we said all the configurations must be even permutation, right? So there are two possibilities. If we focus on corners, either the corners are even permutation or the corners are odd permutation, right? And then the edges follow even and even edges, odd and you do have half and half. And between the two halves, one half is a subgroup. Which one?
What was the identity of that?
Yes, the one was the identity. Plus this one's close, this is not. Right? Okay, what element lives in this pattern? Earlier we talked about commutators. A and A inverse, they have the same parity of permutation, right? You do A and later you do A inverse, no matter whether A lives here or here, it's always even permutation, right? Same with B. So A, B, A inverse, B inverse, always live here, right? That's a commutator. Then the inverse of a commutator is still a commutator, right? So that lives here too. And now a finite string of commutators and their inverses. It's always even, right? It's also lives here, right? Finite strings of commutators and their inverses form a group called commutator group. What I just said shows that commutator group is a subgroup of this subgroup of commutator. Commutator. Now, it turns out that this subgroup actually is as big as this whole half. Don't ask me why. If you ask me, I'll refer you to page 27 of David Singmaster's classic book in 1981 called Notes on the Rubik's Magic Key. They don't ask me. All right, the fact that Rubik's Cube group has such a big commutator group shows that Rubik's Cube is very non-abelian. Because if you have an abelian group, then every commutator is just identity, right? Every group also has a subgroup that's called center, which consists of all elements that commutes with all elements in the group. And we talked about that before, right? The center only has identity and superflip. If you have an abelian group, then all the group elements are in the center, right? The fact that Rubik's Cube group has a very small center also shows that it's very non-abelian. Okay, that's pretty much what I want to share with you today. My son enjoyed the Rubik's Cube thoroughly, me too. I hope this talk will inspire you to go home and pick up a Rubik's Cube and deploy it whichever way you want. Thank you very much for staying with me on this Friday afternoon. You will all have a wonderful weekend.
Any questions? Questions?
So here you said you can generate the whole group using RL, U, D, E, and F. You said we could also take out any one of them and still get the whole group, right?
Yeah,
You said you take out the-
he isn't particular.
Yeah, and then so how does it change like the God numbers of like 20 and 26? If you take out one of them, like do they grow much bigger or you know what I'm saying?
If you restrict yourself to only being able to use those 5 moves.
Then I suppose you will need more steps, right?
Right. Yeah, I guess maybe I was maybe curious like how much bigger it could be or in comparison to only having 20, needing 20.
Oh, well, I guess it will be a lot bigger.
I would presume that when they did the God's move thing, that they considered the cube to be rigid and you weren't allowed to rotate it.
Right.
Yeah, I think you asked a hard question, actually. That could be a very good question. Yeah, because it actually astounds me with all the computer power that we have, how long it actually took them to figure out what it was and really narrow it down. Because it's really not that old.
Yeah.
They've known about it.
Yeah. They discovered 20 in 2010 and 26 in 2014. I mean, not discovered, they proved it. It's recent.
I have a question. Have we classified all the subgroups of the Rubik's Cube group? Do we know all the subgroups? The large group.
Oh my goodness.
I doubt it.
I doubt it too.
I remember playing around when I was an undergraduate or something, and I think I found a couple of the smaller sporadic groups on it. I mean, it's, yeah. But I don't know.
You know how the elements of order 5, 7, or 11 would form?
There shouldn't be, you mean a configuration that?
Yeah, because okay, I think by Cauchy's theorem, there must be, right? Like, I'm seeing like 12 factorial there.
Uh-huh,
So 5, 7, and 11 divide the order of the group. And I'm guessing maybe there are elements of order.
oh, you're right, I made a mistake.
Oh, yeah, there's certainly elements. In fact,
Yeah, you're,
what is the smallest number that for sure there's no element of that order, or no subgroup of that order? Rubik's Cube.
no, thank you very much, I made a mistake. So earlier when I talked about lower U, lower R, I said you repeat doing it 24 times. You have a rotation of 5 corners, right? That one is already order 5. Yeah, you're right, okay. I was wrong.
There's a lot of, and like that, the element of order 1260, there's a lot of them. There's a lot of elements for 1260.
Yeah.
But you know, order 1260 is a super big bargain, given the size of that group, right? Because even the largest order element is tiny compared to the size of the group.
Oh, I also have something cool to show you. Have you seen this before? It's not that. You can put just your fingers too. This one. This one you can have one edge piece flipped. You know why? Because somewhere along the way, you swapped 2 centers. I thought that was pretty cool. Another cool thing to show you. This is 4x4. Only one pair of centers are swapped, which cannot happen on a regular cube. That's pretty cool. Oh, centers are important if you work on a cube with pictures. Because when you move, say for example, you do a DL 105 times, right? 105. So it's not divisible by 4. So centers, they do get moved. They're not moved, they're reoriented. Right? So if you work on a cube with pictures, you do have to pay attention to the centers. Or if you are working on shape mods. Shape mods, they don't look like the normal cube, but if you study it, you'll find, okay, these are my centers, these are my edges, these are my corners. You'll find that they are isomorphic to a normal cube. And then usually in shape mods, you need to pay attention to the centers. So there are algorithms for you to say, turn the front center clockwise, then the upper center counterclockwise, like that. Or turn the upper center 180 degrees, like that.
You can even notice that on the ordinary cube, because most of the cubes have like, one of the centers has like Rubik's Cube or something, yours had something in Chinese written on it. And if you just
Yes.
don't pay any attention to the centers, sometimes you'll notice that when you read it right side up, the red will be on top. And then maybe later the green's on top, right? And so.
Yeah. So centers, they do move around. Now would be one, yes, they do move around.
It's probably too hard to figure out, but so if you randomly disassemble a cube and you put it back together and watch, there's a 1/12 chance that it's solved.
Yes,
Right.
yes,
So
exactly.
if you randomly solve a cube, what's the chance that the centers, probably the centers are all oriented the right way? So if you randomly solve a
It's,
cube with
one
pictures
in-
on it,
It's 1 in 2048 or 1 in 4096. I forget. Here's the one point.
wait, that all of the pieces are oriented that.
Yeah, because I mean, they've got 4 ways to turn on.
Yeah, they're not all independent.
But that's right.
So I figure someone might know it. It's
It's one of those 2 that I just said. and I'll have
One-
to- It's one out of 2048 or 1 out of 4096. If you worry about the pictures, it multiplies the number of combinations by that number. So,
except by power too.
Yeah.
Maybe that.
But you're right, that, you don't have complete freedom on how
Yeah.
you can move it.
Now, how much you create.
Off of what I probably just said, but there's like 1 in 12 chance of like the cube being solvable, like of all the possible. Physical ways the cube could be like oriented, like you could like twist a corner, like that's like physical, like maybe is the group of. The possible physical possible physical configurations 12 times the size of the Rubik's Cube one, or like is. Maybe yes.
It should be. It's probably a semi-direct product.
Yeah, the Rubik's
Direct
Cube is a semi-direct product. You take
Direct.
the subgroup of S12 cross S8 that consists of paired up, they're both even or both odd permutations, right? So that's one piece, and it's a semi-direct product of the orientations, which is cyclic of order, which is 7 copies of cyclic group of order 3 and 11 copies of cyclic group of order 2. And you glue those together in a semi-direct product. And so this was the one you said should contain that Rubik's group, right? So.
A different question. You said that every scramble is an even permutation.
Yes, yes.
But then you also say that every even permutation pieces is a valid scramble.
No, it's.
When we're talking about permutation, we're talking about permutation, permuting the pieces of a solvable cube. Say that again, what's the question?
Well, you described taking apart the cube and assembling it again. If you happen to assemble it, then, I understand. Right, okay.
Which says even I think she means the parity of the permutation on the corners and the permutation sides must match. Right, so it's either an even permutation of the corners and an even permutation of the sides, or it's an odd permutation of the corners and an odd permutation of the sides.
Right.
So if one of them's even and one of them's odd, that's not doable.
Right. Okay, thanks.
And that's what's weird about the thing she showed you with the holes in it, the void cube, because that's a swap of 2 sides, which cannot be done on the Rubik's Cube. And so, you sit there like, well, how can I do it now? Do the same moves, but if you had done the same moves that did that on the Rubik's Cube, you would have permuted some of the centers, so. Okay, others? Well, let's thank Wendy. And the rule of math club is there can't be any pizza left, so, if you can't eat it all, take it back and be the hero of your dorm.
Oh,